Right now, in the middle of the Pacific Ocean, a patch of water is heating up faster than scientists have ever measured. It stretches over 4,000 miles, roughly the distance from New York to Los Angeles and back again. This patch has a name, El Niño. It can change rainfall in Africa, storms in the Atlantic, wildfires in the Amazon, and the temperature outside your own front door. Scientists are calling this one a possible Super El Niño, hotter than the record-breaking events of 1997 and 2015. We will travel from a fishing village on the coast of Peru to burning forests in the Amazon, then follow the jet stream all the way to a heatwave building over your own city. If strange, planet-sized science pulls you in, hit like and subscribe before we start. Get ready. The ocean is about to change everything. Somewhere above the middle of the Pacific Ocean, a satellite is staring down at a patch of water, breaking a record no one wanted broken. This patch churns with heat, boiling just under the surface, invisible to your eyes but glowing bright red on every temperature map scientists check each morning. The water here is running hotter than at any point since global ocean records began, back in 1950. That is over 70 years of measurements, and this summer just pushed past every single one of them. Picture the whole state of Texas. Now imagine an area of ocean 3 times that size, all of it several degrees warmer than it should be. That is roughly the footprint of what forecasters are watching right now, centered along the equator, thousands of miles from the nearest coastline. Buoys bobbing on the surface send readings back every few minutes. Weather balloons rise through the clouds above it. Research ships track its edges. All of them agree on the same unsettling number. The water is now more than 2 degrees Celsius hotter than average, which is almost 4 degrees Fahrenheit. A jump that sounds small until you remember it is spread across an area bigger than the entire United States. Ocean heat like this rarely stays in one place. It bends storms, shifts rainfall, and has already been blamed for droughts on one continent and floods on another in the same season. Scientists have a name for the pattern behind it: El Niño. You have probably heard the term on the news, maybe attached to a headline about wildfires or a strange winter. This year, meteorologists are watching an event developing faster than almost anything on record, a pattern some forecasters are already calling a possible Super El Niño. This version stands apart for one specific reason. Most El Niño events creep up slowly, building over most of a year before anyone notices real effects. This one surged. Temperatures that normally take months to climb jumped in weeks. By the time officials made it official this summer, the ocean had already blown past benchmarks set by the last 3 major events, each of which reshaped weather across the entire planet for more than a year. Something specific caused this shift. Somewhere beneath that glowing red patch on the satellite map, forces have been building for months, quietly reorganizing an entire ocean. Trade winds that normally blow one direction have gone eerily calm. Water that should be piled up on one side of the Pacific has started sliding back the other way. Something switched off, and once it does, the entire system starts to flip. Meteorologists in offices from Tokyo to Melbourne to Miami are checking the same charts every single morning, because whatever happens inside this patch of ocean rarely stays confined to the tropics. A shift here can decide whether a farmer's field gets rain or dust, whether a city's power grid survives its hottest week, whether a coastline gets battered by storms or spared entirely. Few places on the planet remain untouched once a pattern like this one takes hold. To understand how a stretch of open ocean, thousands of miles from land, can end up changing the weather over your own house, you have to go back centuries, to a group of fishermen who noticed something strange happening around the same time every year, long before anyone owned a satellite or a thermometer that worked underwater. Long before anyone tracked ocean temperatures from space, the first people to notice this pattern were fishermen standing on the beaches of Peru, watching the sea for clues about their next meal. Every so often, usually right around the end of December, the water along that coast would turn strange. The cold current the fishermen depended on, the one that dragged nutrient-rich water up from the deep and fed huge schools of fish, would fade out. In its place came warm water, almost bathwater warm, and the fish that fed local villages for generations would vanish along with it. The fishermen gave this warm water visitor a name tied to the timing. Since it tended to arrive close to Christmas, they called it El Niño, Spanish for the little boy, a nod to the Christ child. For a long time, people treated it as a local curiosity, a seasonal guest that showed up. disrupted fishing for a while, then left. Nobody imagined it was connected to storms in Australia, droughts in Africa, or blizzards thousands of miles away in the United States. That changed in the 20th century when scientists began comparing weather records from opposite sides of the planet and noticed something odd. Years when Peru's coastal waters ran warm lined up almost perfectly with years when Australia and Indonesia suffered brutal droughts and when rainfall patterns shifted across huge stretches of Asia and Africa. A pattern that once seemed like a small local story turned out to be one piece of a machine that spans the entire Pacific Ocean, an ocean so large it covers close to a third of Earth's entire surface. Today, researchers call the whole system the El Niño Southern Oscillation, though almost everyone, scientists included, still uses the fisherman's original name for it. It describes an ongoing swing between two opposite ocean states that repeats every few years. In one state, the ocean along South America stays cold and fish-rich, the setup meteorologists call normal conditions. In the other, the water warms dramatically, currents stall, and weather machinery across the globe starts rearranging itself. Roughly every 2 to 7 years, the system tips from one state toward the other, and the whole planet feels it. The economic stakes were never small. Peru's coastal waters, fed by that cold upwelling, support one of the largest fishing industries on the planet, providing food and jobs for millions of people up and down the coast. When El Niño arrives and the fish disappear, entire fishing fleets can sit idle for months, and nations that depend on seafood exports feel the loss almost immediately. Even seabirds felt the shift. Colonies that depended on those same schools of fish sometimes abandoned their nests entirely during a strong event, a warning sign coastal communities learned to watch for long before anyone had a scientific explanation. What actually flips this switch has nothing to do with luck or coincidence, and everything to do with wind. Not a storm, just a steady breeze blowing across thousands of miles of open ocean, so consistent that most people never think about it. That breeze has been blowing across the Pacific for longer than human history has been recorded, quietly deciding where warm water piles up and where it does not. This year, that breeze did something it is not supposed to do, and that single change kicked off everything happening right now. Beneath every El Niño hiding in plain sight is something you have probably felt on your own skin without ever thinking about it. Wind. A steady, quiet breeze that blows almost non-stop across the tropical Pacific, from the coast of South America toward Asia and Australia. Gentle enough to go unnoticed, yet powerful enough to reshape an entire ocean. Sailors noticed this wind hundreds of years ago and used it to cross oceans. Scientists call it the trade wind, and it turns out to be one of the most powerful forces shaping weather on the entire planet. This wind blows so reliably that explorers charted entire voyages around it centuries before engines existed, timing entire trade routes to catch its steady, predictable push across thousands of miles of open water. Losing that predictability, even briefly, was never supposed to happen on the scale scientists are watching unfold this year. That steady westward push does something specific to the ocean beneath it. Blowing steadily westward, it drags warm surface water along with it, piling that warm water up near Indonesia and the western Pacific like a bathtub tilted to one side. On the opposite end, off the coast of South America, that departing warm water gets replaced by cold water, pulled up from hundreds of feet below the surface, a process called upwelling. That cold, nutrient-loaded water is exactly what keeps Peru's fishing ground so rich, and exactly why fishermen centuries ago noticed the moment it disappeared. Above the ocean, the air follows a matching loop. Warm, moist air rises over the western Pacific, dumps rain across Indonesia and northern Australia, then travels east at high altitude before sinking back down over the eastern Pacific, drying out as it falls. This entire loop, wind and rain and rising and sinking air working together, has a name, the Walker Circulation, named for the scientist who first mapped it out in the early 1900s. Think of it as a giant conveyor belt, running east to west along the equator, quietly setting the rhythm for rainfall and drought across an entire hemisphere. Now imagine blowing steadily across a bowl of soup. Keep blowing and the surface tilts, piling liquid against the far side of the bowl. Stop blowing and that tilted surface levels back out, sometimes sloshing hard in the opposite direction. That is essentially what happens when the trade winds weaken. Without a steady breeze holding everything in place, the pile of warm water sitting near Asia starts sliding back east towards South America, and the entire Walker circulation that depended on those winds begins to break down. This year, the trade winds went far beyond a simple slowdown. Across large stretches of the tropical Pacific, they slowed dramatically, and in some areas the wind pattern reversed entirely, blowing warm air and warm water back toward the east instead of holding it in the west. Meteorologists watched it happen in near real time through ocean buoys scattered across the Pacific, each one reporting the same signal over and over. The conveyor belt that has run the same direction for longer than anyone has been alive had started running backward. Once that wind stalls, it sets loose something far bigger than a rearranged surface, something enormous moving quietly beneath the waves, a wall of warm water hundreds of feet down, already racing east across an ocean 12,000 miles wide. Far beneath the surface of the Pacific, invisible to any satellite and undetectable to anyone standing on a beach, an enormous wave has been travelling east for weeks. This wave rolls along more than 300 feet underwater, stretches for thousands of miles, and moves so slowly that a person swimming at a lazy pace could almost keep up with it. Entirely unlike anything you would recognise crashing on a shoreline. Scientists call it a Kelvin wave, and it might be the single most important piece of this entire event. Picture the ocean along the equator as a long hallway filled with two layers, warm water on top and cold water underneath, separated by an invisible boundary called the thermocline. When trade winds weaken, that boundary stops holding steady. A bulge of unusually warm water built up over months near Indonesia starts sliding east along the hallway, riding just beneath the surface. As it travels, it pushes the cold layer deeper and deeper, clearing the path for warm water to take over. This kind of wave does not need a storm to form. It builds slowly from nothing more than a temporary imbalance in wind and pressure, gathering strength as it rolls east week after week. By the time it reaches the far side of the ocean, it can carry enough stored heat to warm an entire coastline for months, all without a single cloud in the sky above it, giving away what is happening hundreds of feet below the surface. The numbers involved are almost hard to picture. In some spots, water sitting between about 150 and 800 feet deep has measured more than 14 degrees Fahrenheit warmer than normal, an anomaly buried far below where sunlight even reaches. That heat did not appear overnight. It built up slowly like a battery charging for months, and this Kelvin wave is the mechanism carrying that stored energy across an entire ocean. It takes roughly 2 to 3 months for a Kelvin wave like this one to cross the Pacific from west to east, gliding along in near silence while the surface above looks almost normal. Researchers track its progress with a chain of moored buoys strung across the equator, each one reporting temperature readings from different depths every single day. Watching those readings arrive week after week is like watching a slow-motion freight train roll toward a station, its cargo completely invisible until the moment it finally arrives. And arrive it does. When the wave reaches the coast of South America, it forces that deep pool of warm water upward, right into the surface layer that fishermen, ships, and coastal cities can actually feel. The cold upwelling that once fed Peru's fishing industry gets buried under a lid of warm water hundreds of feet thick. Surface temperatures spike. The thermocline, once close to the surface and rich with nutrients, sinks out of reach. This is the moment everything changes from a subtle shift in wind patterns into a full-blown transformation of an entire ocean basin. The quiet, deep water wave that spent months crossing an ocean unnoticed finally breaks the surface, and once it does, it tilts the entire sea far beyond the coastline of South America. An ocean that has looked one way for years is about to look completely different. The ocean has a hidden slope to it, even though it looks perfectly flat from an airplane window. Under normal conditions, the trade winds pile so much warm water against the western Pacific that sea level near Indonesia sits noticeably higher, by more than a foot in places, than sea level off the coast of South America. That might sound small, but stretched across an ocean 12,000 miles wide, a foot of tilt represents an almost unimaginable volume of water held in place purely by the steady push of wind. Few people ever think about sea level as something wind can control, since the ocean seems fixed and permanent from any beach or boat. Yet across an ocean this size, even a small, steady push from the wind is enough to hold back an enormous volume of water, the same way a finger pressed against a garden hose can redirect where all the water goes. Once those winds weaken, that tilt cannot hold. The entire slope of the ocean starts to level out, and in the biggest events, it overshoots and tips the other direction entirely. Warm water that spent months piling up near Asia comes sliding back east, arriving off South America as a thick, warm blanket sitting right on top of the ocean. Scientists studying satellite altimeters, instruments that measure the ocean's height down to a fraction of an inch, can watch this slope flatten out in near real time as the shift unfolds. Underneath that warm blanket, the thermocline tells the real story. Normally, off the coast of Peru, the boundary between warm surface water and cold, nutrient-rich water below sits close enough to the surface that wind and currents can easily pull that cold water up. During a strong El Niño, that boundary sinks dramatically deeper, sometimes by several hundred feet, putting the cold, nutrient-loaded water far out of reach. The upwelling that normally happens along this coast essentially shuts off, like flipping a switch on a machine that has run non-stop for years. That cut-off carries consequences far beyond a slower fishing season. The cold water carries far more than low temperature. It is loaded with nutrients pulled up from the deep ocean floor, nutrients that feed microscopic plankton, which feeds small fish, which feed larger fish, seabirds, and eventually the fishing boats that dock along the entire coast of Peru and Ecuador. Cut off the upwelling, and you cut off the base of an entire food chain, all at once, across hundreds of miles of coastline. This year, researchers tracking sea surface height have already recorded some of the flattest, most reversed ocean slopes seen in the modern satellite record, a signal that lines up perfectly with the underwater wave that arrived weeks earlier. Fishing communities that depend on this coastline are bracing for a season that could look nothing like a normal year, and entire national economies that rely on those waters are watching the same data with growing concern. For now, think of the ocean as a tilted table that just leveled out and kept tipping, sending warm water sliding toward a coastline built for cold water. Somewhere above that shifting surface, the atmosphere is about to respond in a way that reaches far beyond any coastline, carrying stored heat out of the ocean and into the sky itself, like a valve slowly opening on a container that has been sealed for years. For years at a time, the ocean quietly stores an almost unbelievable amount of heat. Water absorbs and holds warmth far better than air does, which means the upper layers of the Pacific can soak up energy from the sun for months or even years, without much of that heat ever reaching the atmosphere above it. Scientists sometimes describe the ocean as acting like a thermostat for the entire planet, storing extra warmth during quiet years and releasing it back out during active ones. El Niño is one of the biggest release valves this thermostat has. When warm water that has been building up for months finally rises to the surface across a huge stretch of the Pacific, that stored heat begins radiating upward into the atmosphere almost immediately, warming the air directly above the ocean, then spreading outward as wind patterns carry that warmth across the globe. In a strong event, this release can be powerful enough to nudge the average temperature of the entire planet upward for a full year or longer. The record books confirm this pattern clearly. El Niño years show up again and again near the top of the list for hottest years ever measured. In previous major events, average global temperatures spiked noticeably above the long-term trend, even accounting for the steady warming caused by greenhouse gases building up in the atmosphere over decades. Scientists compare it to opening a valve on a pressure cooker that has been building steam for a long time. The heat was always building underneath the surface, and El Niño is simply the moment it gets released all at once. Researchers have measured this release directly, tracking how much extra heat radiates from the ocean into the atmosphere during a strong event compared to a quiet year. The difference is large enough to show up clearly in global temperature averages within months, a signal so consistent that scientists can often predict a warmer than usual year on Earth simply by watching how strong an El Niño becomes. This year breaks from that pattern in one crucial way. Every previous major El Niño arrived on a slightly cooler planet than the one we live on today. This event is arriving on top of a world that has already warmed by close to 1.5 degrees Celsius, or about 2.5 degrees Fahrenheit, compared to temperatures before large-scale industrialization began. Layer a historic heat release on top of an already warmer baseline, and researchers warn the combination could push global averages into completely uncharted territory. Climate scientists studying this event have said, in plain terms, that humanity has never experienced a strong El Niño arriving on top of conditions this warm to begin with. That statement alone should tell you how unusual this moment is. This year, the ocean's built-in thermostat is releasing stored heat into a system that was already running hot before the valve even opened. What happens next depends on exactly how much heat gets released, and for how long. Early numbers suggest this event is venting far faster than a typical valve opening slowly over months, behaving instead like something that built pressure for years and is now releasing it all at once, faster than almost anything researchers have tracked before, according to the same charts and records meteorologists have kept since the middle of the last century. Every second Thursday of the month, a small team of forecasters at the National Oceanic and Atmospheric Administration release an updated bulletin most people never see, tracking the exact state of the Pacific Ocean down to fractions of a degree. In June, that bulletin delivered a headline meteorologists had been anticipating for months. El Niño conditions had officially arrived, upgraded from a watch to an advisory, the clearest signal the agency issues once a pattern moves from possible to present. Since that announcement, the numbers have only climbed further, accelerating with each new bulletin instead of levelling off. Sea surface temperatures in the key monitoring zone, an area of ocean scientists call the Niño 3.4 region, climbed past 2 degrees Celsius above average by August, translating to roughly 3.5 degrees Fahrenheit, warmer than a typical summer. Forecasters now place the odds above 90% that this event grows into what they classify as very strong before the year ends, one step below the rarest tier scientists track at all. That rarest tier, reserved for only the handful of events that have ever pushed past every previous benchmark, has been reached only a few times since organised record-keeping began, which is exactly why forecasters are choosing their words with such unusual care this year. What has really caught researchers off guard is the speed. A typical El Niño builds gradually across most of a year, giving scientists time to watch each stage unfold. This one has been described by more than one meteorologist as growing faster than anything previously recorded, jumping through intensity categories in a matter of weeks instead of months. Think of a car accelerating from a standstill to highway speed in seconds instead of the usual half-minute. That is roughly the pace difference forecasters are describing between this event and the historic ones before it. Behind these numbers sits a network most people never think about. Hundreds of moored and drifting buoys scattered across the Pacific, satellites orbiting overhead, and specialized aircraft flying directly through weather systems to gather readings. All of that data feeds into supercomputers running dozens of competing forecast models, more than 24 separate systems in some cases, each one independently predicting how the ocean will behave over the coming months. When nearly all of them agree, as they do right now, meteorologists treat that agreement as about as close to certainty as long-range forecasting ever gets. That agreement is what makes this year's bulletins read differently than most. Instead of hedging with words like possible or uncertain, recent reports use phrases like very high confidence, a term forecasters do not use lightly. The ocean and atmosphere are locked together right now in a feedback loop, each one reinforcing the other. Warm water strengthening the atmospheric response, which in turn pulls even more warm water toward the surface. For scientists who have spent entire careers studying this pattern, the current numbers carry a strange kind of significance. Every chart, every graph, every threshold researchers have used for decades to describe a normal El Niño now needs an asterisk next to it, because this year keeps rewriting the upper edge of what those charts were built to measure. To understand exactly how far past normal this event is pushing, it helps to look at the handful of legendary events that used to hold every record on the books. Only a handful of El Niño events in modern history have earned the nickname Super El Niño, a title reserved for the rarest, most extreme versions of this pattern. Scientists point to 3 of them as the gold standard for comparison: the event of 1982, the event of 1997, and the event of 2015. Each one reshaped global weather for well over a year and left behind damage bills stretching into the tens of billions of dollars. Each of those three events reshaped entire industries far beyond weather forecasting. Insurance companies rewrote how they calculated risk. Farmers changed what crops they planted in certain years. Governments built new early warning systems specifically because those three events caught so many people unprepared the first time around, determined never to be caught off guard by an ocean pattern again. The 1982 event caught much of the world by surprise. Arriving before satellites gave scientists the kind of early warning they have today. It brought devastating floods to Peru, drought to Australia and Indonesia, and unusual weather patterns across nearly every continent, all while forecasters scrambled to understand what was even happening in real time. The 1997 event came next, better documented and even more intense, driving global temperatures to what was then a record high and triggering catastrophic flooding in some regions alongside brutal drought in others. Then came 2015, arriving amid a planet already warmed by decades of rising greenhouse gases, pushing that year and the one after it into the hottest years humanity had ever measured at the time. This is the part that has scientists on edge. When researchers compare current ocean temperature readings to where those three legendary events stood at the exact same point in their development, this year's numbers are already running hotter. Water in the key monitoring zone has reached temperatures higher than 1982, 1997, and 2015 all showed at this same stage of the calendar according to the same measurement system used to track every one of those historic events. That comparison does not guarantee this year will end up the strongest event ever recorded. Ocean patterns can still shift, weaken, or plateau earlier than models expect, but it does mean this event is currently on a pace that outstrips every single Super El Niño in the modern record, and some forecast models now suggest a real possibility that this could become the strongest event since organised record-keeping began in 1950, more than 75 years ago. Imagine every Super El Niño ever recorded lined up on a single chart, their temperature curves rising and falling, like mountain ranges drawn side by side. This year's curve is currently tracking above every peak on that entire chart, still climbing, with forecasters expecting it to keep rising for at least another 2 to 3 months before it levels off. For meteorologists who have spent their careers studying 1982, 1997, and 2015 as the benchmark events of their field, watching a new event blow past all three feels less like routine forecasting and more like watching a scoreboard get rewritten in real time. And if this event truly is outpacing the legends, one number in particular is what officially separates it from every ordinary El Niño that never earned the word super at all. Doctors have a simple way of knowing when a fever crosses from mild to dangerous, a specific number on a thermometer. Climate scientists use something similar to separate an ordinary El Niño from the rare version they call super. The line sits at 2 degrees Celsius, about 3.5 degrees Fahrenheit, of sustained warming above average in the Niño 3.4 region, held steady for at least 3 consecutive months in a row. That single number carries enormous weight. A normal human body temperature hovers around 98.6 degrees Fahrenheit. Push that number up by 3.5 degrees, and you are looking at a fever serious enough to send most people to a doctor. The ocean works differently than the human body in almost every way, but the comparison helps explain why scientists treat that threshold so seriously. Cross it, and the entire atmosphere above the tropical Pacific starts behaving differently than it does during an ordinary year. Scientists did not choose that particular number by accident. Decades of historical data show a clear pattern. Events that stay below 2 degrees Celsius tend to produce noticeable but manageable effects, while events that cross above it tend to trigger cascading changes across multiple weather systems at once, each one amplifying the next. It functions less like an arbitrary line on a chart and more like a genuine tipping point, the moment a regional ocean pattern turns into a planet-spanning event. Below the Super El Niño line, weather effects tend to stay regional, noticeable mainly in the Pacific and along nearby coastlines. Cross above it, and the atmospheric response becomes global. Rainfall bands that normally sit over Indonesia and northern Australia shift thousands of miles east. The jet stream, the fast-moving river of wind that steers storms across entire continents, bends into a different shape than usual. Regions that rarely see drought suddenly do, while regions that rarely flood suddenly find themselves underwater. This year's event has already pushed well past that 2-degree line, with readings climbing above 2 degrees Celsius by early August, and forecasters expecting the number to keep rising for weeks. Only a small handful of events since 1950 have ever reached this territory, which is exactly why meteorologists reach for words like historic and unprecedented, instead of their usual, more cautious language. It helps to think of the threshold like the boiling point of water. Heat water slowly, and nothing dramatic happens until it suddenly does, the moment it crosses 212 degrees Fahrenheit and transforms entirely from liquid into rushing steam. Crossing the Super El Niño threshold triggers a similarly dramatic transformation in how energy moves between ocean and sky, unlocking effects that a milder, sub-threshold event simply cannot produce. Scientists are careful to note that crossing this line does not doom every region to disaster. Some places actually benefit from a strong El Niño, seeing welcome rain after years of drought. But the size of the swing, wetter extremes in some places, drier extremes in others, grows dramatically once an event crosses into super territory. And the first place that swing usually shows up is thousands of miles above the ocean itself, in a fast-moving band of wind that most people have heard of but few actually understand, quietly rearranging itself above our heads right now. Roughly 6 miles above your head, far higher than any airplane you have ever flown in, a fast-moving river of wind circles the entire planet, capable of pushing a passenger jet hundreds of miles per hour faster than its engines alone could manage. Meteorologists call it the jet stream, and it acts like a steering wheel for almost every major storm system across North America. Under normal conditions, the jet stream follows a fairly consistent path, dipping and curving but generally staying within a predictable range. That path determines an enormous amount about daily life for millions of people. It decides where cold air from the north gets allowed to sweep south, where storm systems track across the country, and where high-pressure domes settle in and stall out for days or even weeks at a time. El Niño disrupts this river of wind by changing where thunderstorms form over the tropical Pacific. Normally, the biggest cluster of tropical thunderstorm activity sits over the warm water near Indonesia, thousands of miles west of South America. During a strong El Niño, that cluster of storms shifts dramatically eastward, following the warm water as it spreads across the central and eastern Pacific. Since these storms release enormous amounts of heat into the upper atmosphere, moving their location effectively moves one of the jet stream's biggest steering influences right along with them. Picture dropping a heavy stone into the middle of a calm pond. Ripples spread outward from that impact point in every direction, eventually reaching the edges of the pond no matter how far away they started. Shifting the Pacific's thunderstorm cluster works in a similar way, except the ripples are waves of atmospheric pressure called Rossby waves, and instead of a small pond, they spread across the entire planet, nudging the jet stream into a different shape thousands of miles from where the original shift happened. This is exactly how a change in ocean temperature near the equator ends up altering winter storm tracks over the United States, rainfall patterns over California, and even weather thousands of miles away in Europe or Asia. Scientists call these long-distance connections teleconnections, a technical term for something surprisingly intuitive once you picture the rippling pond. Nothing in the atmosphere behaves in isolation. Every piece connects to every other piece, stretched across an entire hemisphere. Forecasters have relied on these teleconnections for decades to make seasonal predictions months in advance, long before any single storm has even formed. Knowing that a strong El Niño tends to push the jet stream south over California, for example, lets meteorologists warn residents about a wetter than usual winter well before the first raindrop falls. That kind of advance warning has saved lives and property across multiple El Niño years, giving emergency planners a head start most other natural disasters never allow. This year, with sea surface temperatures running well above the Super El Niño threshold, the shift in tropical thunderstorm activity has been dramatic enough that forecast models are already showing significant changes to the jet stream's typical summer and autumn position. One of the very first places that shift shows up each year is not over land at all. It shows up above warm ocean water, in exactly the region where hurricanes are born, where a completely different kind of weather war is about to play out. Hurricanes need remarkably specific conditions to survive, and warm water is only the beginning of the list. A developing storm also needs the winds around it, at every altitude from the ocean surface up to the edge of the stratosphere, to blow in roughly the same direction and at roughly the same speed. When that alignment happens, a storm can organize itself into the tight, spinning shape you see in satellite photos. When it does not, the storm gets torn apart before it ever has a chance to strengthen. Meteorologists call this misalignment wind shear, and El Niño is one of the most reliable wind shear generators on the planet. As tropical thunderstorm activity shifts toward the central and eastern Pacific during a strong event, it changes the pattern of upper-level winds blowing across the Atlantic Ocean too, since these systems are all connected through the same rippling atmosphere described earlier. Winds high above the Atlantic often speed up and shift direction during El Niño years, creating exactly the kind of misalignment that shreds a developing storm before it can build any real strength. Imagine trying to stack a tower of blocks while someone repeatedly nudges the table from a different direction every few seconds. No matter how carefully you stack, the tower keeps falling apart before it gets tall. That is essentially what strong wind shear does to a hurricane trying to organize itself. The storm's rotating core gets pushed sideways relative to its own thunderstorms, disrupting the engine that would otherwise let it strengthen into a major hurricane. Forecasters watch this wind shear signal as closely as they watch ocean temperature itself, since a warm ocean without the right wind alignment still fails to produce a dangerous storm. The two ingredients have to line up together: warm water below and calm, aligned winds above, and El Niño has a well-documented habit of removing that second ingredient from the Atlantic, almost entirely during its strongest years. This year, wind shear over the Caribbean Sea has already reached the second highest level ever recorded for early July, according to meteorologists tracking the region. Forecast models covering the heart of hurricane season show the same signature, repeating across the entire main development zone, the stretch of ocean between the coast of Africa and the Yucatan Peninsula, where the majority of the Atlantic's strongest hurricanes typically form. Rising air over the Pacific paired with sinking, drier air settling over the Atlantic has created conditions meteorologists describe as hostile to almost anything trying to strengthen. The result shows up clearly in this year's forecasts. Multiple research teams have lowered their storm count predictions more than once as the season progressed, each update reflecting just how strong this wind shear signal has become. Numbers that started the year in a below-average range kept dropping further as El Niño intensified through the summer months, eventually landing among the quietest seasonal forecasts issued in over a decade. A quieter Atlantic sounds like good news on the surface, and in many ways it genuinely is. Fewer storms generally means fewer coastlines facing evacuation orders, fewer power grids knocked offline, fewer families displaced from their homes, but a season with fewer storms overall does not mean a season with zero risk, and understanding the difference between those two ideas matters more than almost any other lesson buried inside this year's hurricane forecast. Numbers on a hurricane forecast can be deceiving if you only look at the headline. This year, major forecasting teams have converged on a below-average outlook for the Atlantic, with some predictions calling for as few as 7 to 13 named storms across the entire season, a noticeable drop from a typical year. One research group's most recent update pointed toward what could become the fewest storms the Atlantic has seen since 2014, and potentially the fewest hurricanes since 2015. On paper, that sounds like an easy season, and for storm counters keeping a running tally, it likely will be. But meteorologists are quick to point out a detail that gets buried under the good news. It only takes one storm making landfall in the wrong place to turn a quiet season into a catastrophic one for the people who live there. Some of the most destructive hurricanes in American history occurred during years with the overall below-average storm counts, proving that fewer total storms does not automatically translate into fewer disasters. Consider it like this. A school with a low number of car accidents reported over an entire year still has students who get seriously hurt if even one of those accidents happens on their street. The overall number tells you about the season as a whole, not about what happens to any single community that finds itself directly in a storm's path. A hurricane season with only 9 named storms could still produce the single most damaging landfall of the decade, If even one of those 9 storms happens to strengthen quickly and strike a major population centre, history backs up this warning clearly. Some of the quietest hurricane seasons on record still produced individual storms that caused billions of dollars in damage and claimed dozens of lives, simply because that single storm found the wrong stretch of coastline at the wrong time. A low seasonal total has never once guaranteed a safe year for the communities directly in a storm's path. There is another wrinkle buried in this year's numbers that has forecasters paying extra attention. While El Niño tends to suppress the total number of storms across the Atlantic, it does not evenly suppress every storm equally. Storms that do manage to survive the harsh wind shear sometimes find pockets of unusually warm water waiting for them closer to shore, since warm coastal waters in some regions remain above average even during a strong El Niño year. When a storm manages to punch through the hostile upper-level winds and reach one of those warm pockets, it can intensify unusually fast, sometimes within a single day. This combination, fewer total storms but occasional rapid intensification near the coast, has become one of the trickier patterns for forecasters to communicate clearly to the public. A quiet season lulls people into lowering their guard at exactly the moment individual storms can behave unpredictably. Emergency management officials in coastal states have repeatedly reminded residents that hurricane preparation should stay the same no matter what the seasonal outlook predicts, since a below-average season and a dangerous storm are not mutually exclusive outcomes. While the Atlantic settles into this unusual, wind-sheared quiet, something even stranger has been building in that same ocean basin, a pattern so rare that most meteorologists only see it paired with a major El Niño a handful of times across an entire career. Ocean patterns rarely operate in complete isolation, and this year, the Pacific is not the only ocean behaving strangely. Meteorologists tracking the tropical Atlantic have identified a rare cooling pattern developing in the eastern half of that ocean basin, a phenomenon some researchers have started calling an Atlantic Niño, the cooler cousin of the more famous pattern happening thousands of miles away in the Pacific. Most years, the tropical Atlantic simply follows its own quiet rhythm, largely disconnected from whatever the Pacific is doing on the far side of an entire continent. An Atlantic Niño works in roughly the opposite direction from El Niño. Instead of warm water building up near the equator, cooler than average water spreads across the eastern tropical Atlantic, off the coast of West Africa, disrupting the normal balance of temperature and wind across the entire basin. On its own, this pattern would already be noteworthy. Showing up during the same summer as a historic Super El Niño makes it something meteorologists rarely get the chance to study firsthand. Researchers tracking this combination describe it as building a kind of atmospheric shield across parts of North America, a term used to describe how the two patterns working together can reinforce certain wind and pressure setups rather than fighting against each other. The cooler Atlantic waters add to the wind shear already being generated by El Niño, stacking two separate ocean signals on top of each other and pointing them in a similar direction across the same stretch of sky. For scientists, pairing a Super El Niño with a rare Atlantic Niño is a little like watching two separate weather systems roll dice at the same time and land on matching numbers. It does not happen often, and when it does, the combined effect on storm development, rainfall and temperature patterns across the surrounding continents can be more pronounced than either pattern would produce entirely on its own. Forecast models factoring in both signals together have shown even stronger confidence in a suppressed, wind-sheared hurricane season than models looking at El Niño alone. Some researchers studying this rare pairing describe it as a natural experiment that neither computer model nor historical memory can fully prepare for, since so few past years offer a clean comparison. Scientists studying both oceans together say the coming months will likely become a case study meteorologists reference for years afterward. This double signal also complicates long-range forecasting in unexpected ways. Most of what meteorologists know about El Niño's effects comes from studying past events, where the Atlantic behaved in a fairly typical way. With a rare Atlantic Niño layered on top this year, some of those historical comparisons become less reliable, forcing forecasters to lean more heavily on real-time data and computer models instead of simply looking backward at what past Super El Niño years did. While the Atlantic and Pacific play out this unusual coordinated dance, attention has already begun shifting toward a very different kind of weather threat, one that has nothing to do with hurricanes at all. thousands of miles from the tropics, in a region of the country that rarely makes headlines for extreme summer heat, forecasters have started watching the sky for a different kind of invisible danger, one built not from wind, but from a dome of stagnant, trapped air. Most people picture blistering summer heat hitting places like Arizona or Texas, not the misty evergreen forests of the Pacific Northwest. Yet during El Niño summers, this region faces an unusual and specific risk that catches many residents off guard. A much higher chance of powerful, long-lasting heat domes settling directly over Washington, Oregon and parts of British Columbia. A heat dome forms when a large area of high pressure gets trapped in place over a region for days at a time, acting almost like a lid on a pot. Air sinks underneath that lid, compressing and warming as it falls, while the high pressure itself blocks cooler air or storms from moving in and breaking up the pattern. Instead of a normal summer day where temperatures rise and eventually cool off overnight, a heat dome traps heat in place day after day, allowing temperatures to climb higher and higher with each passing afternoon. Many people remember the historic Pacific Northwest heat wave of 2021, when a blocking high-pressure system parked itself over the region and pushed temperatures in Portland, Oregon to 116 degrees Fahrenheit, a reading more typical of Death Valley than a city famous for rain. Roads buckled under the heat, power cables melted. Hundreds of people died from heat-related illness in a region where most homes were never built with air conditioning, since summers there had rarely required it. That single event reshaped how an entire region thought about summer. Cities that had never needed widespread air conditioning began installing it by the thousands. Building codes changed. Emergency cooling centres, once rare in a region famous for mild weather, became a standard part of summer planning almost overnight, a direct response to just how deadly a single blocking high-pressure system had proven to be. El Niño summers raised the odds of exactly this kind of blocking pattern forming over the Pacific Northwest, specifically, more so than in nearby California or the interior Southwest. Those southern regions tend to run warmer during El Niño years, mainly because of elevated background ocean temperatures and long-term climate trends, without necessarily needing a dramatic high-pressure blocking pattern to do it. The Pacific Northwest is different. Its El Niño risk comes specifically from a higher chance of the atmosphere locking into place and refusing to budge for days or even weeks. This year, with the ocean tracking toward historic Super El Niño territory, meteorologists studying the pattern have flagged an elevated potential for exactly this kind of blocking event later in the summer and into early autumn. A region already grappling with drought conditions and dry vegetation from a warm spring becomes significantly more vulnerable once a heat dome settles in, since extreme heat dries out remaining moisture in plants and soil within days, turning entire forests into ready fuel. That combination, trapped heat above and drying vegetation below, rarely stays separate for long. Once a region grows hot and dry enough, all it takes is a single spark, whether from lightning, a downed power line, or human carelessness, to turn a heat dome into something far more destructive. And this year, the world did not even need to wait for the Pacific Northwest version of that story to play out, because a different fire record had already fallen months earlier, before this El Niño had even finished forming. By the end of April this year, months before El Niño officially reached advisory status, the entire planet had already set a record nobody wanted to see broken. Researchers tracking global fire activity confirmed that the world had burned more land during the first 4 months of this year than during any January through April stretch ever recorded. Massive fires tore through West Africa and the Sahel region, while major outbreaks also struck India, Southeast Asia and parts of China, all before the ocean pattern driving this story had even fully developed. Firefighters and emergency crews on multiple continents were already stretched thin months before peak fire season typically even begins. Aircraft and resources normally held in reserve for the hottest stretch of summer were deployed early, leaving less backup available if conditions worsen later in the year exactly as forecasters expect, with El Niño's influence still building toward its eventual peak. That timing matters enormously to the scientists studying it. A record-breaking start to global fire season, arriving before El Niño's effects had really kicked in, suggests the underlying conditions for extreme fire risk were already dangerously primed heading into summer. Add a historic, fast-strengthening Super El Niño on top of that starting point, and researchers warn the back half of the year could push global fire activity into territory nobody has measured before. El Niño influences wildfire risk through several connected pathways at once. Shifting rainfall patterns dry out vegetation in regions that normally rely on consistent seasonal rain. Higher overall temperatures pull moisture out of soil and plants faster than usual, turning green landscapes into dry fuel more quickly than in an average year. Changes to wind patterns, driven by that same jet stream shift discussed earlier, can also create the kind of dry, gusty conditions that let a small fire spread explosively once it starts. Picture a forest as something similar to a stack of firewood sitting outside all summer. A little rain now and then keeps that wood too damp to easily ignite. Cut off the rain and add weeks of extra heat, and that same stack of wood dries out completely, ready to catch fire from something as small as a single spark. That is essentially what has been happening across huge stretches of the planet this year, well before this El Niño had even reached its current historic strength. Scientists studying the connection between climate change and wildfire risk stress, an important detail buried inside this story. El Niño alone rarely starts a fire. Human activity does that, whether through lightning strikes hitting dry vegetation, unattended campfires, or sparks from equipment and power lines. What El Niño changes is how far and how fast those fires spread once they ignite, by drying out the landscape and creating exactly the kind of conditions that turn a small, containable fire into an uncontrollable one within hours. With a record already broken before this year's El Niño had even peaked, researchers have shifted their attention to specific regions they consider are most vulnerable heading into the rest of the year. One of those regions sits at the heart of the entire planet's climate system, a rainforest so vast it helps regulate weather patterns across multiple continents, and this year, that rainforest is facing conditions scientists have been dreading for years. Stretching across roughly 2.5 million square miles, an area larger than the combined size of every country in the European Union, the Amazon rainforest does something no other ecosystem on Earth does at the same scale. It produces staggering amounts of oxygen, stores carbon equal to years of global fossil fuel emissions locked inside its trees and soil, and generates so much of its own rainfall that scientists sometimes describe it as breathing, exhaling moisture that falls right back down as rain across the same region. Some of that same moisture eventually travels far beyond South America entirely, feeding rainfall patterns as distant as the middle of the United States, which means a stressed, drought-stricken Amazon can ripple into weather thousands of miles from the region itself. That self-sustaining rain cycle depends on a delicate balance. Trees release moisture into the air through their leaves. That moisture forms clouds. Those clouds produce rain, and the rain feeds the same trees that started the cycle in the first place. Disrupt that balance badly enough, and the whole system can start working against itself, with drier conditions leading to fewer clouds, less rain, and even drier conditions the following year. El Niño disrupts this balance directly. During strong events, shifting rainfall patterns typically reduce the amount of moisture reaching large parts of the Amazon basin, sometimes dramatically. Previous major El Niño years have coincided with some of the driest, most fire-prone stretches the Amazon has experienced in the modern record, turning normally lush, moisture-soaked forest into landscape dry enough to burn. This year's historic Super El Niño has researchers particularly concerned, since the rainfall reductions tied to past events tend to scale up alongside the overall strength of the pattern. A stronger El Niño generally means a bigger disruption to the rain cycle feeding the Amazon, and this event is already tracking above every previous Super El Niño at the same point in its development. Combine that with the record-breaking global fire activity already recorded earlier this year, and scientists studying the region describe the upcoming months as a critical stretch worth watching closely. It is worth being precise about what actually causes fires inside the Amazon, since the drought itself rarely strikes the first match. Logging roads, land cleared for agriculture, and human activity remain the primary sources of ignition across the region. What a severe El Niño drought does is remove the natural fire resistance that a healthy, moisture-rich rainforest normally provides, allowing fires that start along cleared edges to spread deeper into untouched forest than they otherwise could. Researchers studying the Amazon have warned for years about a theoretical tipping point, a threshold beyond which repeated droughts and fires could push large sections of rainforest to convert permanently into drier grassland, unable to recover its original ecosystem even after rain eventually returns. Nobody knows exactly where that tipping point sits, and this year's event will not answer that question on its own, but a rainforest already stressed by years of deforestation, facing one of the strongest El Niño droughts on record, is exactly the kind of scenario scientists have been warning could push parts of the Amazon closer to that edge than ever before. Half a world away, on a continent famous for its extreme relationship with fire and drought, an entirely different kind of record is also coming into view. Australia has one of the longest and most detailed weather records of any country in the Southern Hemisphere, with meteorologists tracking El Niño's effects on the continent all the way back to 1900. In that stretch of more than 125 years, the country's Bureau of Meteorology has documented 27 separate El Niño events, giving Australian scientists an unusually deep well of historical data to compare against whatever happens next. The connection between El Niño and Australian weather runs almost exactly opposite to what happens in South America. While warm Pacific water brings rain and flooding risk to Peru and Ecuador, that same shift in the water circulation pulls moisture away from Australia and Indonesia entirely. Rising air and rainfall that would normally sit over northern Australia shift thousands of miles east, following the warm water toward the central Pacific, leaving sinking dry air behind across huge stretches of the Australian continent. The results tend to follow a familiar and painful pattern. Major past El Niño events have coincided with some of Australia's worst droughts and most destructive bushfire seasons on record, including fire seasons that burned tens of millions of acres and blanketed entire cities in smoke for weeks at a time. Farmers across the country's agricultural regions have learned to watch Pacific Ocean temperature reports almost as closely as meteorologists do, since a strong El Niño often signals a coming season of failed crops and dwindling water supplies. Water restrictions during past strong events have forced major cities to ration supply for months at a time, while rural communities dependent on rainfall for drinking water and irrigation have sometimes gone without reliable access for an entire season, a hardship that tends to strike hardest in the country's most remote and vulnerable regions. This year, with El Niño tracking well above the intensity of any of those previous 27 recorded events, Australian officials have begun raising unusually direct warnings. Forecasters have pointed toward the real possibility of the country's hottest spring on record, a season that in Australia runs from September through November, arriving right as El Niño's influence over the Southern Hemisphere typically reaches its peak. Combined with already dry conditions across parts of the country, officials are warning of a heightened risk for both severe drought and dangerous bushfire activity heading into the final months of the year. Bureau of Meteorology scientists have described this event as tracking into territory the country's historical record simply has not seen before, a statement that carries real weight given how far back that record actually extends. Comparing current ocean and atmospheric data against previous benchmark years, several indicators are already running beyond the range covered by any of the 27 previous events on file, forcing forecasters to rely more heavily on physical modelling than direct historical comparison. For a country that has spent more than a century learning to live alongside this cycle of Pacific-driven drought and fire, an event this far outside historical norms represents uncharted ground. Firefighting agencies across multiple states have already begun adjusting seasonal staffing and resource plans in anticipation of what officials are calling an unusually dangerous stretch ahead. While drought tightens its grip across the Australian continent, an entirely different kind of danger has been unfolding underwater, far from any coastline, in a part of the ocean most people never think to check on at all. Far beneath the waves, in shallow sunlit water most people only ever see in photographs, an entire ecosystem is quietly cooking. Coral reefs cover less than 1% of the ocean floor, yet they support roughly a quarter of every species living in the sea, an entire underwater metropolis built from creatures that look like rock but are actually alive. A coral polyp survives through a partnership with microscopic algae living inside its tissue. Those algae capture sunlight and share the energy with their coral host, and in return, the coral gives the algae a safe place to live. That same algae is also what gives coral its brilliant colour. When ocean water gets too warm for too long, the coral panics and expels its algae partner, leaving behind a pale, ghostly skeleton. Scientists call this bleaching. A bleached coral still clings to life at first, slowly starving without its algae partner, and if the heat does not ease quickly, it will not survive. The world just lived through the most widespread bleaching event ever recorded. Between the years 2023 and 2025, heat stress severe enough to trigger bleaching struck reefs in more than 80 countries, pushing roughly 84% of the planet's coral reefs into the danger zone. Researchers called it the fourth global bleaching event in recorded history, and by far the worst. Normally, reefs get a few years to recover between major heat events, riding out a cooler La Niña phase before the next warm cycle arrives. This year offers no such break. With this El Niño arriving so soon after the last global bleaching event, forecasters at NOAA's Coral Reef Watch program issued an outlook in July placing much of the planet's reef systems at high risk for renewed bleaching between August and November, raising the very real possibility of a fifth global event before the fourth one has even finished playing out. El Niño makes this threat worse in more than one way. Beyond simply warming the water, it also lowers sea level across the Western Pacific as water piles up on the opposite side of the ocean, sometimes exposing shallow reefs to open air and harsh sunlight during low tide, adding direct sun damage on top of heat stress the coral is already fighting to survive. Divers and marine biologists monitoring reefs this year have already reported early warning signs in multiple ocean basins, patches of coral turning pale weeks before the official forecast window even opens, a preview many researchers had hoped would arrive later, not sooner. Recovery, when it happens at all, unfolds unevenly. Some fast-growing coral species can regain their colour within weeks once water temperatures drop. Slower-growing species, some of which took centuries to build the massive structures divers photograph today, can take up to a year to recover, if they recover at all. Scientists warn that repeated bleaching without enough time to heal between events can push a reef past a point of no return, a threshold beyond which even the toughest coral species stop coming back. Nobody knows exactly where that threshold sits for any individual reef, which is exactly what makes this year's outlook so unsettling to the researchers watching it unfold. While reefs fight for survival underwater, a different kind of survival story has been playing out along the coast of South America, where an entire industry depends on creatures far smaller than coral and far more sensitive to a warming ocean. Off the coast of Peru swims a fish smaller than a human hand that quietly supports one of the largest fisheries on the planet. The Peruvian anchovy rarely grows longer than 6 inches, yet together, in schools that can stretch for miles, these small fish form the base of an industry worth billions of dollars a year and supply roughly 1/5 of the entire world's fish meal, the ground-up fish protein that feeds farmed fish, chickens and pigs across the globe. That entire industry depends completely on the cold, nutrient-rich upwelling described earlier in this story, the same current that fishermen centuries ago watched vanish every time El Niño arrived. This year, it vanished again, and the fishery is already feeling the strain. Peru's Fisheries Authority set this year's catch limit at just under 2 million metric tons, the lowest quota in a decade and a drop of more than 1 million metric tons from the previous year's allowance. Even that reduced quota has proven difficult to fill. Regulators repeatedly suspended fishing entirely this year after surveys found an unusually high number of juvenile fish in the catch, a warning sign that the population is struggling to reproduce normally in the warmer water. One suspension stretched into another, then another, leaving boats tied up at dock and landings sitting at a fraction of what officials had expected by this point in the season. For the thousands of families whose income depends directly on these boats, every extended suspension translates into lost wages that do not simply return once fishing resumes, since a shortened season rarely makes up for weeks spent tied up at dock. Coastal towns built entirely around the anchovy trade feel these gaps first and hardest, long before the losses ever show up in a national economic report. El Niño has devastated this fishery before, and recent history shows exactly how bad it can get. A previous strong event cancelled an entire fishing season outright, a disaster industry veterans called the worst in decades, one that cost more than $1 billion in lost export revenue in a single year. With this year's event already tracking toward historic strength, similar losses are becoming a real possibility once again. the ripple effects reach far beyond Peru's coastline. Fish meal prices have already climbed to some of the highest levels ever recorded, making it more expensive to raise farmed fish, chickens and pigs in countries thousands of miles away that have never heard of the Peruvian anchovy. Aquaculture operations across Asia and Europe, many of which rely on this single fishery for a huge share of their feed supply, are already adjusting budgets and searching for substitutes that do not yet exist at the same scale. Wildlife feels the collapse just as sharply as any industry does. Seals, sea lions, and seabirds along Peru's coast depend on these same schools of fish to survive, and during past strong El Niño events, malnourished and starving animals have washed ashore by the thousands, unable to find enough food and water that no longer supports the food chain it once did. An industry, an entire coastline of wildlife, and a global supply chain, all thrown off balance by a shift in a handful of degrees of ocean temperature. And half a world away, an entirely different set of lives, more than 1 billion of them, waits anxiously each year for a very different kind of water. The rain that is supposed to arrive with the summer monsoon. Every summer, more than 1 billion people across South Asia depend on a single weather system, arriving roughly on schedule. The monsoon, a seasonal shift in wind direction that drags moisture off the ocean and dumps it across the Indian subcontinent, delivers most of the region's entire yearly rainfall in just a few months. Farmers time their planting around it. Reservoirs that supply drinking water to hundreds of millions of people fill almost entirely because of it. When the monsoon runs short, the consequences reach almost every part of daily life across an enormous stretch of the planet. El Niño has a well-documented habit of interfering with this system. The same eastward shift in tropical thunderstorm activity that reroutes hurricanes in the Atlantic and dries out Australia also tends to weaken the monsoon winds that normally pull moisture toward India, pulling that same rain-bearing energy toward the Central Pacific instead. Meteorologists at India's National Weather Agency have already forecast a below-normal monsoon this year, projecting seasonal rainfall at roughly 90% of the long-term average, with a meaningful chance the season falls into officially deficient territory. Farmers across the region watch these early season forecasts with a mixture of dread and cautious hope, since planting decisions made in the opening weeks of the monsoon can determine whether an entire harvest succeeds or fails months later. A forecast calling for below-normal rainfall does not guarantee disaster in every district, but it does mean millions of farmers are entering this planting season with less certainty than usual, adjusting which crops they choose to plant based on how much rain they now expect to receive. History offers a useful, if imperfect, guide here. 2 of the strongest El Niño events on record delivered significantly reduced monsoon rainfall to India, contributing to serious agricultural losses in both years. Yet one of the most intense El Niño events ever measured produced a surprisingly close to normal monsoon, largely because a separate ocean pattern in the Indian Ocean happened to counteract El Niño's usual drying effect that particular year. That single exception tells forecasters something important. Another player besides El Niño helps decide India's fate each summer. That other player lives in the Indian Ocean itself, a temperature seesaw between its western and eastern halves that can either fight against El Niño's influence or pile right on top of it, depending on which way it swings. This year, forecasters have watched that second pattern closely, since its behaviour over the back half of the monsoon season could end up mattering nearly as much as El Niño itself, in deciding whether India's harvest comes up short or manages to scrape by close to normal. For the farmers and families depending on this rainfall, the stakes could hardly be higher. Rice, a crop that feeds more people than almost any other on Earth, depends heavily on monsoon rainfall across the region. So does wheat planted later in the year, once monsoon soil moisture has replenished exhausted farmland. A season that falls even 10 or 15% short of normal can mean the difference between a stable harvest and a genuine food security crisis for millions of households living close to the margin. While one ocean pattern threatens to starve an entire subcontinent of rain, the very same shift in global wind patterns is doing the exact opposite thousands of miles away, delivering far more rain than usual to a region already struggling with extremes of its own. Weather rarely plays fair, and nowhere does that show up more clearly than when comparing East Africa to its neighbours across the Indian Ocean during a strong El Niño. While India worries about a monsoon running dry, communities across Kenya, Somalia and Ethiopia often brace for the opposite problem entirely. Rainfall arriving in such enormous quantities that rivers overflow, roads wash out, and entire villages find themselves underwater. This split personality traces back to the same giant loop of rising and sinking air introduced earlier in this story, the Walker circulation, now playing out on the far side of the planet from where it usually operates. Normally, that loop keeps rain concentrated over Indonesia and the Western Pacific, while leaving East Africa comparatively dry. During a strong El Niño, the entire loop shifts eastward, and part of that shift drags unusually moist air toward the Horn of Africa during the region's short rainy season, which typically runs from October through December. The results can swing from welcome relief to genuine catastrophe within the same event. A past strong El Niño triggered catastrophic flooding across East Africa, displacing hundreds of thousands of people and destroying roads, homes, and farmland across multiple countries at once, even as those same months brought devastating drought to Indonesia and parts of Australia thousands of miles away. Two regions, one shared ocean pattern, two almost opposite disasters unfolding at exactly the same time. Aid organisations that operate across both regions have learned to prepare for this split well in advance, stockpiling flood relief supplies for East Africa at the very same moment they position drought assistance for Indonesia and Northern Australia, since a single strong El Niño reliably demands both kinds of response within the same handful of months. Few natural disasters ask relief agencies to plan for flood and famine simultaneously using the exact same seasonal forecast. Yet that is precisely the balancing act this particular ocean pattern forces onto humanitarian planners nearly every time it strengthens. Forecasters tracking this year's event expect a similar east versus west split to play out again. Seasonal outlooks published by the World Meteorological Organization point toward wetter than normal conditions spreading across the Greater Horn of Africa, along with parts of Central Asia, Southern Europe, the Western United States, and Southeastern South America, while the familiar dry pattern settles back over Indonesia and Northern Australia, reinforcing the drought risk already building there. For communities in East Africa, more rain is not automatically good news. Years of below-average rainfall in the region have left soil compacted and rivers running low, conditions that actually make flash flooding worse once heavy rain finally does arrive, since dry, hardened ground struggles to absorb water quickly. Emergency planners across the region have learned to treat an approaching strong El Niño as a genuine flood warning, not simply a chance for the drought to finally break. This single pattern, one shift in ocean temperature near the equator, manages to threaten India with drought, flood East Africa, and dry out Australia, all within the same handful of months. It is one of the clearest demonstrations of just how far a change in one small stretch of ocean can reach, rearranging the fate of harvests and homes across three separate continents at once. And in the Indian Ocean itself, a second, quieter ocean pattern has been building all year, one capable of making every part of this story even more extreme. Hidden within the Indian Ocean is a second climate pattern that most people have never heard of, yet it can dramatically amplify or soften everything El Niño does across an entire region. Scientists call it the Indian Ocean Dipole, and like El Niño, it comes down to a simple temperature seesaw, this time stretched across the width of the Indian Ocean rather than the Pacific. During what researchers call a positive phase, the western half of the Indian Ocean, off the coast of East Africa, runs warmer than average, while the eastern half, near Indonesia, runs cooler than average. That temperature difference reshapes rainfall across the entire basin in a way that should sound familiar by now. Warmer water in the west tends to boost rainfall over East Africa, while cooler water in the east suppresses rainfall over Indonesia and Northern Australia, reinforcing exactly the pattern El Niño already tends to produce in both places. When these two ocean patterns align in the same direction during the same year, their combined effect on rainfall and drought can be considerably more extreme than either pattern acting alone. Researchers studying past years when a positive Indian Ocean dipole coincided with a strong El Niño have documented sharper flooding in East Africa, deeper drought across Indonesia and Australia, and even measurable effects on public health, food security, and local conflict across vulnerable communities throughout the wider region. This year's forecast carries real uncertainty about exactly how these two patterns will interact. global climate agencies tracking ocean conditions expect a positive Indian Ocean dipole to develop later this year, potentially reinforcing El Niño's effects across the Indian Ocean rim during the back half of the season. Regional forecasters focus specifically on India's monsoon, meanwhile, have described conditions as closer to neutral heading into the peak of the rainy season, creating genuine disagreement among experts about exactly how much extra punch this second pattern will add and precisely when. Satellites and ocean buoys stationed across the Indian Ocean track this second pattern with the same careful attention scientists give to the Pacific, watching for the telltale temperature seesaw that signals whether a positive phase is truly taking hold. Every update from that monitoring network gets folded directly into the same seasonal outlooks meteorologists issue for East Africa, India and Australia, making the Indian Ocean dipole a quiet but essential piece of forecasting an entire region's fate. That uncertainty matters enormously to millions of people living across the region. A positive Indian Ocean dipole arriving on schedule could mean the difference between a merely below normal monsoon and a genuinely severe one. It could also mean the difference between a normal wet season in East Africa and a repeat of the catastrophic flooding seen during past years when both ocean patterns fired together at full strength. Scientists studying these compounding effects describe the relationship between El Niño and the Indian Ocean dipole as one of the more difficult forecasting puzzles in modern climate science, precisely because the two patterns do not always move in lockstep, and their combined effect depends heavily on timing that can shift by weeks or months. What remains certain is that two separate ocean basins, thousands of miles apart, are both leaning in directions that could intensify a year, already shaping up to be one of the most extreme in decades, a trend showing up clearly in a completely different measurement: the average temperature of the entire planet. 2 years ago, Earth recorded its hottest year since organised global temperature tracking began roughly a century and a half ago. Scientists at NASA, NOAA, and several other major research agencies around the world all confirmed the same result independently, comparing measurements gathered from thousands of weather stations, ocean buoys, and satellites circling the planet. That record has stood since, but this year it is under serious threat. Through the first half of this year, monthly global temperature readings have repeatedly landed among the warmest ever measured for their respective months, with June ranking as the second warmest June on record, trailing the record year by only a fraction of a degree. Scientists analysing this data note that the strengthening El Niño arrived at almost exactly the same point in the calendar as it did during the previous record-setting year, and the 2 years have been tracking remarkably close to each other in overall ocean warmth ever since. Multiple independent research teams have run the numbers and landed on strikingly similar conclusions. Current best estimates give this year roughly a 3 in 5 chance of finishing as the second warmest year ever measured, trailing only the existing record. A smaller but still meaningful chance exists that this year could overtake that record entirely, a possibility that has climbed steadily as El Niño has continued strengthening faster than expected throughout the summer. Every major research group tracking global temperature, including agencies in the United States, Europe and Canada, has converged on remarkably similar conclusions despite using different methods and different networks of measurement stations, a level of agreement that adds real confidence to forecasts still months away from being confirmed by actual full-year data. That kind of independent agreement across multiple national agencies rarely happens by coincidence, and it tells researchers the underlying signal driving this year's warmth is strong enough to show up clearly no matter which data set a scientist happens to be using. One detail has climate scientists paying especially close attention to what comes next. El Niño's warming effect on the atmosphere typically does not peak immediately. Historical patterns show the biggest boost to global average temperature usually arrives roughly 6 months after the ocean pattern itself reaches its strongest point. With this event forecast to peak sometime between September and November, the full weight of its warming influence may not fully show up on the world's thermometers until sometime in the first half of next year. That timing detail carries an unsettling implication. Even if this year ultimately falls just short of setting a new record, the year that follows could end up considerably hotter still, riding the delayed wave of heat this event is currently building up. Multiple forecasting groups have already begun projecting that next year could push the global average temperature meaningfully higher than any year humanity has ever recorded. A preview built directly from how this year's event has been behaving so far. None of these numbers exist in isolation from everything happening across the planet right now. The wildfires already breaking records, the coral reefs bleaching for a second time in barely 2 years, the fisheries collapsing off Peru, and the monsoon struggling to reach India all trace back to the same underlying story. An ocean releasing enormous stored heat directly into a planet that was already running warmer than at any point in recorded human history before this event even began. Behind every conversation about record heat sits a single number that international climate negotiators have spent decades trying to avoid crossing. 1.5 degrees Celsius, or about 2.5 degrees Fahrenheit, of warming above the temperatures Earth experienced before large-scale industrialization began roughly 2 centuries ago. That number, enshrined in a landmark international climate agreement, was meant to serve as a warning line. A threshold scientists warned would sharply increase the risk of extreme weather, ecosystem collapse, and rising seas if crossed for any sustained period. Negotiators chose that particular number after years of scientific review, weighing the difference between a planet that stayed below it and one that pushed past it for good. Every fraction of a degree beyond that line was projected to bring measurably worse consequences, from stronger storms to faster ice melt to steeper losses for crops and coral reefs already living close to their physical limits. Crossing that line for a single year does not mean the world has permanently failed to meet that international goal, since the agreement is built around long-term averages measured across decades, not any individual 12-month stretch. Still, a single year spent above that threshold carries real weight as a warning sign, a preview of the kind of world that becomes the normal baseline once the long-term average eventually catches up to it. According to the World Meteorological Organization, there is now a very high likelihood, estimated at more than 90%, that global average temperature will temporarily exceed that 1.5 degree threshold during at least 1 year between now and the end of the decade. There is also a strong likelihood that at least one of those same years will surpass the current hottest year ever measured, breaking a record most scientists assumed would stand for several more years at minimum. This year's historic El Niño sits at the centre of that likelihood. Long-term warming from greenhouse gases has already pushed the planet's baseline temperature dangerously close to that threshold, even during quiet, NECU-neutral years. Layer a historic heat release from the Pacific Ocean on top of that already elevated baseline, and crossing the line becomes far more likely than it would during any ordinary year. Climate scientists studying this event describe the collision as something genuinely new in recorded human history. Every previous major El Niño occurred against a cooler background climate than the one the planet currently sits on top of. This event is testing, in real time, exactly what happens when one of the most powerful natural heat release valves on the planet fires at close to full strength on top of a baseline that has never been this warm before. The consequences of that collision rarely stay confined to a single number on a chart. Warmer baseline ocean temperatures feed stronger, wetter storms. Once they do form, they dry out vegetation faster, accelerating the same wildfire risk already breaking records this year. They push coral reefs past survival thresholds more easily and more often. Every regional story covered so far in this account, from bleaching reefs to a struggling monsoon to a starving anchovy fishery, becomes measurably worse the higher that underlying baseline climbs, which is exactly why scientists are watching this particular collision of El Niño and long-term warming with such unusual concern. Every chapter of this story so far has covered places most viewers will never personally visit. The deep Pacific, the coast of Peru, coral reefs, the plains of India. None of it stays confined to distant coastlines and faraway oceans. Somewhere in the details already covered, there is very likely a piece of your own summer hiding in plain sight. Ask someone what caused an unusually smoky week last month, or why farmed shrimp cost more at the store this summer, and most people would never think to connect either answer back to a patch of warm water sitting thousands of miles out in the Pacific Ocean, even though that connection runs directly and provably back to exactly that source. Maybe it showed up as smoke. Wildfires burning thousands of miles away can send smoke drifting across entire countries, turning ordinary summer skies hazy and orange even in cities nowhere near an active fire. Maybe it showed up at the grocery store, where the price of shrimp, farmed salmon, chicken, or pork crept up slightly this year, a ripple effect traced all the way back to fish meal prices spiking after Peru's anchovy season collapsed. Maybe it showed up as an unusually brutal heat wave in a region that rarely gets that hot, the kind of stretch that keeps making local news for days at a time. Even something as mundane as a family vacation can end up tangled in this story. A quieter than usual Atlantic hurricane season might make a coastal trip feel safer this year, while a region bracing for its hottest spring on record might mean outdoor plans somewhere else get rearranged entirely. Nobody sends a notification explaining that a shift in Pacific Ocean temperature is the reason a cookout got smoky, or a grocery bill crept higher than expected, yet the connection sits there all the same, quietly threaded through an ordinary day. Scientists who study these far-reaching connections describe them as teleconnections for a reason. The same term introduced earlier when explaining how the jet stream carries ripples of atmospheric pressure clear across the globe. Weather does not respect borders, oceans, or distance. A shift in water temperature near the equator can rearrange rainfall over an entire continent, reroute a hurricane, or nudge a heat wave into a city that has never dealt with one before, all without anyone in that city ever hearing the words El Niño mentioned on the local news. This year's event carries an unusually large reach precisely because of how strong it has become. Milder El Niño years tend to stay mostly confined to their classic textbook regions. An event tracking toward the strongest category ever recorded tends to spill much further outside those usual boundaries, touching regions and seasons that a weaker version of the same pattern would likely have left alone entirely. Understanding that reach matters for more than just curiosity. It means paying attention to seasonal forecasts this year carries real, practical value, whether that means preparing for a smokier summer, budgeting for slightly higher grocery bills, or simply understanding why the weather outside your own window has felt just a little bit off all year. And for anyone wondering what comes next after summer fades, the pattern's biggest, most dramatic act is still ahead of it, arriving right on schedule with the first cold fronts of winter. Everything covered so far has unfolded during the part of the year when El Niño's grip on global weather is actually at its weakest. Summer effects tend to stay relatively contained, mostly limited to hurricane suppression, tropical rainfall shifts and regional heat risk. Winter is a different story entirely. Once cold weather season arrives in the Northern Hemisphere, El Niño's influence on daily weather grows dramatically stronger, reshaping storm tracks across North America in ways that show up on almost every local weather forecast for months at a time. The reason comes back to the jet stream, the fast-moving river of wind introduced earlier in this story. During a strong El Niño winter, that river typically splits and shifts south, dragging a more active southern storm track across California, the desert southwest, and the Gulf Coast states. Regions that spend a normal winter relatively dry can suddenly find themselves under repeated storm systems, sometimes triggering flooding, mudslides, and heavy mountain snow in places built for a much quieter season. Reservoir managers across the drought-prone western United States actually welcome this shift in some respects, since a wetter than usual El Niño winter can refill water supplies strained by years of below-average snowfall. That same welcome rain, though, arrives with real risk attached, since soil scorched by wildfire earlier in the year loses much of its ability to absorb water quickly, turning heavy rainfall into dangerous mudslides across burn-scarred hillsides within hours. Meanwhile, the northern tier of the United States and much of Canada typically experience the opposite effect, milder temperatures and reduced storminess as the coldest air stays locked farther north than usual. This split pattern, wet and stormy in the south, mild and quiet in the north, has repeated closely enough across past strong El Niño winters that meteorologists consider it one of the most reliable seasonal forecasting tools available anywhere in weather science. With this year's event forecast to remain at very strong intensity well into winter, carrying odds above 90% according to the latest agency outlooks, forecasters expect a particularly textbook version of this winter pattern to take hold, and possibly an amplified one given how far this event has already outpaced previous benchmark years. California in particular has a well-documented history of major flooding during the strongest El Niño winters on record, a pattern water managers and emergency planners across the state are already preparing for months in advance. The rare Atlantic Niño pattern introduced earlier complicates this otherwise familiar picture. Because that cooling pattern in the Atlantic remains an unusual wild card layered on top of a historically strong El Niño, some of the typical winter rules meteorologists rely on could behave slightly differently than in past textbook years, forcing forecasters to lean more heavily on real-time model data, rather than simply assuming this winter will unfold exactly like the legendary events of the past. For millions of people across North America, this winter forecast carries direct practical stakes, from ski resorts hoping for a banner snow season in the mountains, to farmers worried about flooded fields, to homeowners in fire-scarred hillsides bracing for mudslides once heavy rain finally arrives. Behind every one of those local stories sits the same distant ocean pattern that started this entire account, still building strength and still reshaping how an entire winter across an entire continent is about to unfold. Every part of this story eventually reduces down to a dollar figure somewhere, whether anyone realizes it or not. Economists who study past El Niño events have tried to calculate the total cost these patterns impose on the global economy, and the numbers involved are almost as staggering as the weather itself. Researchers at a major American university analysed decades of economic data following the two strongest El Niño events of the 20th century, and estimated that each one cost the global economy trillions of dollars, with effects on economic growth still measurable years after the ocean itself had returned to normal. That kind of economic damage rarely arrives as a single dramatic event. It builds gradually, through thousands of smaller disruptions stacking on top of each other across multiple industries at once. The Peruvian anchovy collapse alone drained more than $1 billion from export revenue during one particularly severe past season, a loss that rippled outward into higher feed costs for fish farms, poultry operations and pig farms on completely different continents, raising grocery prices for consumers who had never heard of the fishery responsible. Agriculture absorbed some of the heaviest blows. Strong El Niño years have historically coincided with price spikes in rice, wheat and palm oil, three crops that together feed a huge share of the planet's population, since major growing regions across India, Southeast Asia and Australia can all face drought stress during the very same season. When multiple major food-producing regions struggle simultaneously, global supply tightens fast, and prices at grocery stores thousands of miles from any affected farm start climbing within months. Insurance markets feel the pressure just as directly. Companies that price flood, wildfire and storm risk closely track ENSO forecasts, adjusting premiums in regions expected to face elevated danger during a strong event. Homeowners in wildfire-prone stretches of the western United States, flood-exposed parts of California, and drought-stricken agricultural regions worldwide have all seen insurance costs shift in response to forecasts like the ones driving this year's headlines. Even industries that seem completely unrelated to weather end up affected indirectly. Shipping companies reroute cargo around storm tracks that behave differently than usual. Energy companies adjust production forecasts based on expected heating and cooling demand across entire regions. Tourism boards in coastal areas brace for either a banner season or a disastrous one, depending on which side of El Niño's rainfall split their particular coastline happens to land on. Governments themselves are not immune to these costs either. Agencies that manage disaster relief, agricultural subsidies, and emergency water supplies often see their budgets stretched thin during a strong El Niño year, forced to redirect funding toward flood response in one region, while simultaneously supporting drought-stricken farmers in another, sometimes within the very same national budget. Multiply that strain across dozens of affected countries at once, and the true cost of a single historic ocean pattern becomes almost impossible to calculate with any real precision. These costs rarely arrive as a single dramatic headline the way a hurricane landfall or a wildfire evacuation does. They spread quietly instead, worked into supply chains, insurance premiums and grocery store shelves in ways most people never trace back to their true origin. A shift of just a few degrees in the temperature of a stretch of ocean thousands of miles away, still working its way through the global economy long after the headlines about the ocean itself have faded. Weather decides far more than whether crops grow or fisheries survive. It also decides, in ways most people never think about, how far diseases spread and how many people they reach. Mosquitoes, the tiny insects responsible for spreading illnesses like dengue fever, malaria, and Rift Valley fever, breed almost entirely based on water and temperature conditions, which means a pattern capable of rearranging rainfall across entire continents inevitably rearranges disease risk right along with it. The connection works differently depending on which side of El Niño's rainfall split a region ends up on. In areas facing unusually heavy rain, like East Africa during a strong event, pools of standing water left behind by flooding create ideal breeding grounds for mosquitoes almost overnight, and outbreaks of mosquito-borne illness have historically followed close behind major flooding events in the region. A serious outbreak of Rift Valley fever, a disease that spreads between livestock and humans through mosquito bites, followed directly on the heels of severe East African flooding during a previous strong El Niño year, sickening thousands of people and killing livestock across multiple countries. Health workers responding to that outbreak had to move quickly across a landscape reshaped almost overnight by floodwater, setting up emergency clinics in areas that had rarely dealt with mosquito-borne illness at that scale before, a scramble that taught public health agencies across the region valuable lessons about how fast this kind of outbreak can spread once conditions turn favourable. In regions facing drought instead of flooding, the mosquito connection works through a different mechanism entirely. When reliable water sources dry up, both people and mosquitoes end up concentrated around the same limited supply of remaining water, whether that means a shrinking well, a slow-moving river, or water stored in open containers around homes. That forced closeness between people and mosquito breeding sites can drive disease transmission upward, even in places experiencing far less rainfall than usual. Researchers studying decades of health records across South and Southeast Asia have found measurable links between ENSO conditions and outbreaks of cholera and dengue fever, tracing changes in disease rates back to shifts in local temperature and rainfall driven by the broader ocean pattern. The relationship is not always simple or predictable, since local factors like sanitation infrastructure, vaccination coverage, and public health response capacity all shape how a given outbreak actually unfolds once conditions become favourable for it. Public health officials in vulnerable regions have started treating strong ENSO forecasts as an early warning system in their own right, stockpiling medical supplies, expanding mosquito control programs, and preparing hospital capacity months before disease case counts actually start climbing. That kind of advanced preparation, built directly on the same seasonal forecasts driving headlines about hurricanes and drought, has already helped some regions blunt the worst potential impact of past strong events. This year's historically powerful El Niño, combined with the added influence of the Indian Ocean dipole across parts of Asia and Africa, has health officials in multiple countries watching disease surveillance data with particular care. An ocean pattern that can already reroute hurricanes, dry out entire continents, and flood others has one more consequence layered underneath all the others, one measured not in dollars or degrees, but in outbreaks that public health workers hope this year's early warnings can help them get ahead of. None of the forecasts described throughout this entire story happened by guesswork. Behind every confident prediction about this year's El Niño sits an enormous, largely invisible scientific operation that has been quietly tracking the Pacific Ocean for decades, refining its tools every single year to catch the earliest possible signs of a pattern like this one forming. The system relies on two very different approaches working together. Dynamical models simulate the physical laws governing ocean currents, wind, and heat exchange using some of the most powerful supercomputers on the planet, essentially recreating a miniature version of Earth's atmosphere and ocean inside a machine and running it forward in time to see what happens next. Statistical models take a completely different approach, searching through decades of historical weather data for patterns that resemble what is happening right now, then predicting the future based on what happened after similar setups in the past. Forecasters combine dozens of both types of models together, weighing their combined output to produce the confidence levels that show up in official bulletins. One of the earliest and most reliable warning signs comes from exactly the place described earlier in this story. The the deep, invisible layer of ocean heat riding beneath the surface on a slow, moving Kelvin wave. Scientists tracking subsurface ocean temperature have learned that unusual warmth building hundreds of feet down often shows up months before the surface itself displays any obvious change, similar to feeling a floor begin to vibrate slightly before a distant train ever comes into view. That early subsurface signal gave forecasters a genuine head start on this year's event, flagging unusual warmth building beneath the surface well before the ocean's surface temperature confirmed what was coming. This combination of tools has transformed El Niño forecasting dramatically compared to just a few decades ago. Earlier major events, including the historic 1982 event, caught much of the world almost completely by surprise, since the scientific tools available at the time could not detect a pattern like this one until its effects were already unfolding in real time. Today's forecasters routinely flag a developing El Niño many months in advance, giving farmers, fishing fleets, emergency planners, and public health officials genuine lead time to prepare before the worst effect actually arrive. That advance warning has measurable value well beyond convenience. Farmers who know months ahead of time that a weak monsoon is likely can shift toward more drought-tolerant crops before planting season even begins, while coastal communities bracing for an active hurricane season can stock emergency supplies long before the first storm ever forms. Prediction accuracy still varies considerably, depending on how far in advance a forecast reaches. A prediction covering the next month tends to prove highly reliable. A prediction reaching a full year into the future carries far more uncertainty, since small errors in a model's starting conditions can compound significantly the further forward in time a simulation runs. Even with dozens of sophisticated models working in close agreement, as they currently are for this year's event, meteorologists are careful to note that long-range forecasting will never reach the kind of precision available for tomorrow's local weather report. Even with every tool described here working together at their absolute best, this entire scientific system still runs into a wall every single year, around the same point on the calendar, a blind spot researchers have never fully managed to see past. Even the most sophisticated forecasting system in the world has a season it consistently struggles with. Meteorologists call it the spring predictability barrier, a stretch of the calendar, roughly March through May in the Northern Hemisphere, when forecasts about whether an El Niño will develop later that year become dramatically less reliable than forecasts made at any other point in the annual cycle. Scientists have studied this blind spot for decades and still do not fully agree on exactly why it happens, though most suspect it relates to how the ocean and atmosphere transition between seasons in ways that are inherently harder to model with precision. That barrier is not the only mystery buried inside this story. Not every El Niño behaves the same way, even when the underlying ocean temperature numbers look similar on paper. Researchers have identified distinct flavors of the pattern, depending on exactly where in the Pacific the warmest water ends up concentrated. A classic textbook event warms the eastern Pacific most strongly, close to South America, producing the effects described throughout most of this story. A different version, sometimes called a Central Pacific event, concentrates its warmth farther out toward the middle of the ocean instead, and can produce meaningfully different, sometimes even opposite, effects in certain regions compared to a classic Eastern-flavoured event. Telling these flavours apart early enough to matter for forecasting remains a genuine scientific challenge, since the distinction often only becomes fully clear once an event is already well underway. Getting the flavour wrong in an early season forecast can mean predicting drought for a region that ends up flooding instead, or the other way around, a real limitation that keeps meteorologists humble even during years when their broader ocean temperature forecasts prove remarkably accurate. Some researchers suspect this year's event leans closer to the classic Eastern-flavoured variety, given how strongly the warmest water is concentrated near South America rather than spreading evenly across the middle of the ocean. Even that classification carries some uncertainty this early in the event, since flavours can shift subtly as an El Niño matures, occasionally blending characteristics of both types before the season is finished. An even bigger question looms over the entire field, one scientists are actively debating rather than agreeing on. As the planet's oceans continue absorbing heat from decades of rising greenhouse gas emissions, researchers are trying to determine whether extreme El Niño events like this one are becoming more frequent. a genuine possibility supported by some climate modelling studies, but still far from settled science. Other research suggests the frequency might stay roughly similar, while the intensity of individual events simply climbs higher, riding on top of an already warmer ocean baseline. Distinguishing between these possibilities and figuring out which one actually describes the coming decades remains one of the most actively studied open questions in modern climate science. The core mechanics driving El Niño, the trade winds, the Kelvin wave, the thermocline, all remain well understood and thoroughly documented through decades of careful measurement. What remains genuinely uncertain is how those familiar mechanics might behave differently as they operate on top of a rapidly changing planet, an open question this year's historic event may end up helping to answer, one data point at a time. And for anyone wondering what happens once this particular event finally loses its grip on the Pacific, history offers a fairly consistent, if occasionally surprising, answer. No El Niño lasts forever. Every event eventually loses strength, and the pattern almost always swings towards something else entirely, rather than simply fading back to a calm, neutral ocean. Understanding what typically comes next matters just as much as understanding the event itself, since the transition can carry its own set of dramatic weather consequences. History offers a fairly consistent pattern to work from. Looking back across every Super El Niño event since 1970, the overwhelming majority were followed almost immediately by a shift into La Niña conditions within a year or two. The cooler, opposite phase of the same ocean cycle. Some researchers describe this relationship as a kind of natural seesaw, where an unusually strong warm phase essentially exhausts the stored ocean heat driving it, setting the stage for conditions to swing hard in the opposite direction once that heat has been released. Several forecasting groups tracking this year's event have already begun projecting exactly that kind of rapid reversal. Multiple computer models point toward a swift decline in El Niño's strength once Northern Hemisphere spring arrives next year, with some projections showing at least even odds of La Niña conditions developing by the middle of next year, an unusually fast turnaround for an event currently tracking toward record intensity. Ocean scientists studying this potential swing point to the sheer amount of heat this year's El Niño has already released as one reason a fast reversal seems plausible. An event this intense draws down the stored subsurface warmth that fuels it unusually quickly, and once that reservoir of heat runs low, the entire system can lose momentum far faster than a milder, slower building event ever would, setting up conditions for a swing in the opposite direction sooner than forecasters might otherwise expect. La Niña essentially flips the entire script covered throughout this story. Where El Niño tends to bring a wetter, stormier winter to the southern United States and a milder one to the north, La Niña typically reverses that pattern, delivering colder, wetter winters across the northern tier of the country, while the south often turns drier than usual. Atlantic hurricane season, suppressed so dramatically this year by El Niño's wind shear, typically roars back to life during a La Niña year instead, since the very same wind patterns that shredded storms all summer tend to relax once the pattern flips. Not every transition follows the textbook timeline, and recent history offers a clear reminder of just how unpredictable this system can be. A previous La Niña event defied typical expectations entirely, persisting for 3 consecutive winters in a row rather than the usual single season, an outcome so unusual that meteorologists gave it its own nickname to describe how rare a 3-year stretch like that actually is. That extended stretch produced its own chain of extreme weather consequences across multiple years, proving that even well-understood ocean patterns can occasionally behave in ways that catch even veteran forecasters off guard. Whether this year's historic event follows the more typical rapid rebound into La Niña, or takes a longer, less predictable path, remains one of the genuine open questions forecasters are watching closely as the year progresses. What seems far more certain is that the Pacific Ocean, having just delivered one of the most extreme warm events in the modern record, is unlikely to simply settle back into quiet, unremarkable conditions anytime soon. Stack every chapter of this story together, and a bigger, more unsettling question starts to take shape. Is an event like this one, historic, record-breaking, and arriving on top of an already warming planet, a rare outlier the world just happens to be witnessing this particular year? Or is it a preview of what El Niño will simply look like from now on? as the planet's oceans continue absorbing heat decade after decade. The reefs described earlier in this story offer one of the clearest warning signs pointing toward the second possibility. Coral reefs traditionally needed several years of calmer conditions between major heat events to recover, rebuilding their algae partnerships and regrowing damaged structures before the next stress event arrived. This year's likely bleaching event follows barely 2 years behind the most severe global bleaching event ever recorded, an unusually short gap that some researchers directly connect to a broader pattern of El Niño and La Niña events, transitioning into each other faster and less predictably than they used to. Fisheries tell a similar story. Peru's anchovy industry has now weathered multiple severe El Niño disruptions within a relatively short stretch of years, including one cancelled season and repeated suspensions during this year's event alone, leaving less recovery time between shocks than the industry historically depended on to rebuild fish populations and financial reserves. Scientists studying long-term ocean temperature trends note that the baseline the entire ENSO cycle now operates on top of has shifted dramatically higher than it stood even a few decades ago. Every El Niño, even a relatively modest one by historical standards, now unfolds on top of ocean water that starts out warmer than the water that fueled the legendary events of the past. That shifted baseline alone could explain why recent events keep pushing past benchmarks that once seemed like reasonable upper limits for how intense this pattern could realistically become. Communities and industries built around the old rhythm of this cycle, expecting a predictable stretch of calm years between major events, are already being forced to rethink those assumptions. Fishery managers, coral reef conservationists, and disaster planning agencies across multiple countries have begun revising their own recovery timelines, no longer assuming the multi-year breathing room between major events that past generations could once count on. Researchers remain genuinely divided on how much of this represents a true long-term shift in the underlying pattern versus natural variation that simply looks dramatic within any single decade of data. Climate systems this complex rarely reveal their long-term trends clearly within just a handful of years, and scientists are careful to avoid declaring a permanent new normal based on one historic event, however dramatic it appears while it is actually happening. What almost every researcher studying this event does agree on is less about certainty and more about direction. Whether or not this exact pattern repeats every few years going forward, the underlying trend of a warmer ocean baseline is not expected to reverse anytime soon, which means future El Niño events, whenever they arrive, will very likely keep unfolding on top of conditions warmer than anything the historical record has previously measured. Understanding exactly what that means for reefs, fisheries, monsoons, and communities across the planet remains one of the defining challenges facing climate science over the coming decade, starting with this very event still playing out right now. Everything in this story traces back to a single, simple fact. Water holds heat, and when enough of it gathers in one place, it does not stay quiet for long. A patch of the Pacific Ocean, invisible to almost everyone on the planet, warmed by a few degrees, and that small shift rippled outward until it touched nearly everything covered across this entire account. It rerouted hurricanes away from the Atlantic while quietly stacking wind shear so high that entire coastlines caught an unexpected break this season. It reached into the sky itself, bending the jet stream and threatening a heat dome over a region famous for its rain rather than its heat. It reached underwater, cooking coral reefs that had barely begun recovering from the worst bleaching event ever recorded. It reached into fishing boats off the coast of Peru, into rice paddies across India, into flooded villages in East Africa, and into grocery store shelves thousands of miles from any ocean at all. It reached the health of newborn seals starving along the coast of Peru, the price of a bag of shrimp at a grocery store checkout counter, the smoke drifting over cities that will never see the ocean responsible for it, and the quiet worry of a farmer in India watching clouds that refuse to arrive on schedule. Every one of these threads connects back to the same shift in temperature, in the same stretch of open water, thousands of miles from anywhere any of these people have ever stood. Along the way, this single ocean pattern pushed global temperature records to the edge of being broken, collided with a planet already warmed dangerously close to an internationally agreed upon danger line, and set the stage for a year that may not even reveal its full impact until sometime next year, once the delayed warming finally catches up with the headlines. It carried genuine scientific mysteries too, blind spots in forecasting that decades of supercomputers and satellites still have not fully solved, and open questions about whether events this extreme are becoming the new normal on a warming planet. What happens next remains, in true El Niño fashion, both remarkably well understood and still genuinely uncertain. Forecasters expect this event to keep strengthening through autumn, before eventually peaking sometime between September and November, followed by a likely decline and a possible rapid swing toward La Niña sometime next year, though history has already shown this system is more than capable of surprising even its most experienced observers. For now, the numbers keep climbing. Every second Thursday of the month, that same small team of forecasters releases another bulletin, another update on an ocean pattern currently rewriting the upper limits of what scientists thought this cycle could do. Whether this year ultimately goes down as the strongest El Niño ever measured, or simply one of the strongest, may not be fully settled until long after the headlines have moved on to whatever comes next. One thing remains true, regardless of how the final numbers eventually shake out. A stretch of ocean most people will never see, thousands of miles from any coastline you or I have ever stood on, has spent this entire year proving just how tightly connected this planet actually is. Watch the sky above your own house a little differently for the rest of this year. Somewhere out in the middle of the Pacific it is still listening,